like that, spin round slowly, and then they cut them all out to make one big long picture. Well, of course we can do that in software, and that's really probably where the biggest step forward has come from, is in the speed of computers and the algorithms inside. So if you give me two pictures, one picture taken from here and one picture taken from there, and they're both looking at the same object or a similar object, I can join those pictures together electronically. Now we'll come on to what software does that in a minute, because I encourage you to have a go at it yourself. You only need a camera, and you only need a computer, and you can upload it online to one of the clouds, press the button, and you'll get your stitched image or your 3D modelled image come back. But the fundamental thing about photogrammetry, and that's the Wikipedia definition of it, is the art, science, technology of retaining reliable information about physical objects and the environment through the process of recording, measuring, interpreting photographic images and patterns. What a load of words to me, not a lot really. But what we are doing is lots of models in here and so on. There's a car outside, okay? Just take the car as an example. I walk up to the car and I look at it from one direction. I've only got one photograph of it because I'm not allowed to move. What information do I know about that car? I'm not really aware of the depth, because the perspective may be hidden from me. All I know is that there's two wheels on one side and it's sort of shaped like that. That's all I really know. But if I'm then allowed to walk 10 feet that way, 10 feet that way, and then I look at the car, now I have much more information. And that's exactly what happens in photogrammetry. So if you can take an object and you can photograph from many, many different points around that object, then you can stitch them all together into one single image. Well, how do you do that? Because it's not flat, right? If I walk around the car, how do I stitch those together? Any suggestions on that? Well, I can do it on a ball, I can do it on a sphere. So if I've got a sphere like that, I can take all those images and put those images onto the sphere, and then I can stick them together. And that's exactly what this software does as well. So by joining all these together, when you come to join them together, it doesn't necessarily mean that they're going to fit particularly well, because you might need to turn one slightly because it's at a different angle. If I look at the car from that angle and I look at the car from that angle, then in the software I need to correct for the fact that that picture has come from a different angle. So each one of those pictures inside that software is looking at the image and is moving that picture about in software until it finds a point where they match. And when they match, that's when it does the stitching operation and it brings them together. How do you find out inside an image whether two points correspond to each other? In other words, how do I know the fifth wheel nut on one side in one image is the same as the fifth wheel nut in the other image? How do I know that? Well, that's what the software is good at, because it looks at the statistics which are around there. It looks at whether a red pixel is next to a green pixel, which is next to a blue. It's doing all manner of clever things. But in the end, what it does is it knows that that point in that image is the same as that point in that image. Now you do that for lots and lots of different images, and you come up with a situation. So down the bottom, here's a load of still images that someone took of, say, for example, that jawbone. If you're allowed to move the jawbone, it's a different ball game, because you can put it onto a spinning table. I particularly like cake decorators' tables. So you spin it round and you just leave the camera in one place and take lots and lots and lots of pictures of it. And the tool that we use is Photoscan Anti-Soft, and it's a nice package. You can get a student license for a few £100, but that's probably beyond anyone's wish to do it in here just as a casual hobby. But what you can do is you can take your digital camera and you can upload it. Jim, you know some good sites, don't you?
Yeah, drag and deploy. It's a free service. You can just upload them and get the model back free. There are few free services out there, yeah.
So you don't need to think about this process at all. You just take your camera, you take lots of shots with that camera, and you upload those still images to this particular site, and what you get back is a 3D model. Now, what's a 3D model look like? Well, a typical 3D model has two main components to it. It has a wire mesh. So you've all seen those when they sort of show you how they made Jurassic Park and things like that. So you've got a wireframe mesh which is representative of the structure of the device, and on top of that you then paste the texture afterwards. And in this Photoshop, or Photoscan rather, you can see these different layers, and Jim will show you some demonstrations of that in a little while. But down the bottom, you've just got the collection of JPEGs that went in to make up that image. So there's lots and lots of images, but taken from different vantage points. That's important. So if I modelled a car, unless I crawled on my hands and knees and photographed underneath the car, I would have no knowledge of what was underneath the car, because I don't have a photograph of it. So I can't stitch it together, so I can't make a model of it. When you fly over a field or something, and most of you here know, I think, that when you get structure in the ground, you see circles, you see raised ridges, all this kind of stuff. That's what we're looking for when we do the photogrammetry. So fly over somewhere, we may see no structure at all. But as soon as you look at the 3D model of it, suddenly what you can see are raised embankments. And you saw some in the crops, didn't you, when the crop was high?
Yes, the crop circles, yeah.
So you can actually see circles where you've got a fully grown crop. I'm not talking about different coloured pieces of grass like they used to discover archaeology in the past. You're actually talking about different heights in the crops. And when you bring that back and process it, you end up with a terrain model, which is the shape of the land, and you end up with rings in it because the crop hasn't grown quite so well for the usual reasons, because of the drainage of the soil and so on underneath. So there's kind of magic. Whenever you do anything like this, the results that you get, more often than not, aren't quite what you expect. And Jim's been doing some lovely stuff down at the boating lake up at East Mersey, and really verifying, before they flooded the seawall, where the sea level was going to come. And it was spot on, wasn't it? You could even tell that there was a little mound in the middle, wasn't there, that wasn't part of their plan, but we saw that long before they flooded it with the sea. So, that's the principle behind it. You put one of these in the air, or you walk about with the camera. Point it towards the ground, keep walking, that's fine, as long as you've got something which is different. So if you just point down and photograph chunks of grass or something, that's going to be very hard to stitch that together. If you photograph water, it's going to be very difficult to stitch together. Tarmac, gravel stones, anything like that. But as soon as it's got structure, so for example, I can produce a model in here relatively easily, point the camera, so I go click, 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 click like this, and I just keep going forwards and backwards across the audience like this. I might do a few up here, I might do a few down there. When we put it through this software, what we'd end up with is we'd end up with something that looked roughly the shape, but of course I wouldn't be able to see your legs from over there. So you wouldn't have any legs in the model. The model would just be like this, so I'd see the hills going up and down and so on. Okay, so there are limitations to it, but for archaeology, when you're flying at a known height over a site that you're interested in, it is very, very revealing indeed. So here's an example inside one of these pieces of software. So probably not a lot of meaning to most of you, but what you have here is the location in the 3D world where that photograph has been taken from. And you can see, if you look closely, that they're not actually all flat. Some of them are like that, some of them are like that. So in other words, what happened when that picture was taken, because these aren't perfect, the drone was, or it was like that. So what the software is doing is it's actually correcting for the error that the drone made, which is fascinating. And in doing that, what it starts off with is it's trying to create a series of points so it can stitch them together. That's the first stage. Once it's done that, then it can start to create 3D terrain models on it. Jim, do you just want to say a bit about sparse point cloud?
Yeah, well, this particular model is
Sorry. Don't hold it too close.
this particular model is of what we know is of Man Field in East Mersey. We've been working with UCL and the Citizen archaeological teams, and this was a model we made of the archaeological dig that was happening this summer at East Mersey. As John was explaining, this is the photogrammetry process. This is the first stage, which we call the sparse point cloud. Going on with the processing, we come up with the dense point cloud, and you can clearly see that it's a lot more makes a lot more sense now, and that is the dig that took place. The blue markers are quite important. We went round the field with a very accurate GPS, which is all tied into Ordnance Survey's grid. This gives the model a real-world footing. It's geo-referenced to the real world.
So just to be clear about what that means, so you've got a series of images that are all stitched together, like you cut out with a modelling knife, and they're all in one place, but the thing is, where those blue dots are, we know that they're correct to the real world. We know they're accurate to sort of that much in X, Y, and Z, and that's important because the software isn't perfect. So what the software now needs to do with the knowledge of those blue points is just warp itself a little bit to fit those blue points. Because the blue points are right, but the assumption of joining the pictures together isn't perfect. So the more of those control points you have, the more accurate that is on the ground. Notice accurate rather than precise, but we won't go into what the differences are between those. But it is very, very accurate when you have those ground control points. Now you don't have to have it to produce a meaningful image with some ups and downs and some circles in the middle or whatever, because you'll still know where it is within a few 5 centimetres, 10 centimetres, something like that. But for work to do with things like seawalls, nuclear power stations, things like this, you need to know, well, less than that. You know, it's got to be very, very accurate indeed. So that's something that Jim's been doing for a while. He's been adding these control points in and producing maps which are astonishingly accurate and probably some of the best in the area.
The GPS accuracy is to about 1 centimetre, so we expect that the model to be within probably twice that. 20 millimetres is a very good accuracy that we would expect.
And that's also in Z, which is the complex one. So you've got the X direction, Y direction, but the up-down from satellites, that's the difficult one to get accurate, and that's the one that everybody is really trying to achieve the most accuracy in. But the more control points you have, the more accurate a model is.
Yes, so this is the 3D model, obviously without the...
I was just going to say, Jim, that ball in the middle, do you want to explain that ball? Because that
That's
always
just-
throws